Good afternoon, class. Happy snow day. Starting a new unit this week on boundary layers, actually viscous drag, I'll say. We're going to start this week, Tuesday and Thursday, talking about boundary layers, which will lead to a drag component we're going to refer to, as skin friction. Skin friction. And we can think just simply about the idea of taking a flat plate like this and running water over it like this, or air. It will give rise. Skin friction is the drag imparted on the surface of the plate here by the fluid moving over it. So it's a tangential force. It comes from the motion of the water or air that's parallel to the body. It is the form of drag that is dominant in aerodynamic or streamlined objects like a submarine, for example, or an airplane fuselage and wing. They have other drag components as well, which we'll be talking about, but that is the largest drag component for those streamlined vehicles. When we talk about ships, skin friction at lower Froude number will be the dominant form of drag, and at higher Froude number, we'll see that the wave drag is typically the highest form of drag. So today I want to talk about what the skin friction comes from. It's going to be associated with boundary layers. These boundary layers are going to be divided into two regimes. One is a laminar regime, one's a turbulent regime, and every property of the boundary layer will be tied to the Reynolds number, including whether or not it's laminar or turbulent. And so we'll be invoking Reynolds number a lot today. So we've been talking about just dividing the idea of ship resistance into these four pieces. So here's the drag on the ship, total drag on the ship. There are three pieces that come from integrating the pressure field over the body, and that pressure integral is non-zero, resulting in a drag force. That will be the wave drag. Drag due to waves. We introduced last week the dynamics of waves and the Kelvin wake associated with the ship. We're going to be using some tools to look at wave drag, and we'll talk about how we use models in order to get the wave drag on a full scale by scaling up the model resistance. In a coming unit, we'll talk about induced drag. This is drag due to lift, and associated with viscous effects is what's called the viscous pressure drag, but it manifests itself in terms of a pressure integral over the body. And we'll be talking about that next week. Viscous pressure drag, even though it's a clunky name, it's simply due to having a bluff object, flow moving over it, and the flow separates from the body. You get these vortices behind it. You can think about a truck, Big Mack truck moving down the highway. You can think about when you look at a flow over baseball, football, looking in the water by a bridge and seeing the eddies that form in the piling that's holding the bridge up. That's all due to the fact that the body is not streamlined. The flow separates from the body, but the reason for that flow separation is due to viscosity in the fluid. It's due to an interaction of the boundary layer and the pressure gradients, which we'll talk about next week, but it manifests itself in terms of a non-zero pressure integral. So that I put it under the category here of pressure. Then we have tangential drag, like skin friction, that comes from the boundary layer and shear stresses associated with that boundary layer. And that's the subject of this week, Tuesday and Thursday. So you think about the simple problem of flow over a flat plate. We have this uniform velocity, which created somehow. This is a flat plate at the bottom here. So it's 2D. Think about it as 2D. And these are just parcels of fluid that are moving at this point at the same speed. So they all have the same momentum because we assume the density is the same as well. Once they strike this plate, the key thing here is that the fluid that touches the plate doesn't move at all. This is what we refer to as the no-slip condition. So it doesn't allow the fluid to move at all. So the momentum of this particular parcel here at the very bottom is brought to a halt. It's brought to zero. And so at this moment, we still have some momentum of the parcel above it. So these parcels haven't had any influence from what's happened to that lower parcel. But because fluid isn't allowed to just slip along itself due to viscosity. And there's different mechanisms here that are going to cause a vertical. So in this direction, we'll call Z. There'll be a mixing of U momentum. Sorry, there's kind of a delay between my iPad and the screen here. U momentum. So this is the U momentum is in the X direction, but we're thinking about how that varies in Z. And there's going to be an exchange going on among these parcels. There's always an exchange among these parcels of this momentum. When you're dealing with a laminar boundary layer, like we're talking about today, that exchange just comes through simple Fickian diffusion. So just think about if you have hot and cold, even something solid like a desk in front of you, and you put a hot cup of coffee sitting on the desk and you measure the temperature a foot away from the cup of coffee, over time it will rise because heat is diffused through that salt or whatever your desk is made of through your desk. Heat is diffused through the desk through collisions, random collisions of molecules within the desk. This tends to be a pretty slow process because it relies on this collision of molecules. But there is heat diffusing throughout the desk. This is also a diffusive process that we're talking about here, but it's diffusion of momentum. And so momentum is diffused among these parcels at relatively low rates in this laminar case. And we'll contrast this with the turbulence case on Thursday, where the diffusion is through a different mechanism, which are eddies in the flow. A much more rapid mixing of momentum occurs. In laminar boundary layers, this is a slow process, but it's always in play. And so this bottom parcel, which still exists here, there's still fluid here, it's just not moving. And it is exchanging, it's basically pulling momentum from the parcel above it. So the parcel above is leaking momentum into this parcel. And so sometime later, you still have no motion here. And this parcel's lost some momentum, and we can stack the rest up here. And you can start to see that the influence of the wall in the form of the no-slip condition is now starting to feel its way out into the flow. But it's taken some time because the parcels have moved from left to right. They're moving at a speed u out here in the external flow. So there's a time scale associated with this motion from left to right. And that time scale we can write as delta x, the distance they've traveled in that time, divided by the speed at which they're moving. So there's still diffusion going on, and now there's an interchange between these two parcels we'll think about. So up here, these parcels, they're exchanging momentum, but because they have the same momentum, their individual momentums don't change. Down here, their momentums are different. So momentum likes to mix things. I'm sorry, diffusion likes to mix things, keep them the same. That's what diffusion likes to do. It's trying to make the diffusion between these the same. But this second parcel here is still exchanging momentum with the zero momentum parcel here. And this will give rise to a slowdown. If this is number 3, 2, and 1, this means now 3 is going to be slowed down. Sorry about the delay. It's going to take a second here to appear. 3, 2, 1. And so sometime later here, we have still 0 at the wall, or slower 2 parcel. 3 has now been slowed down. And number 4 is still as is. And you can kind of play this game forever. But you're imagining the real fluid isn't made of individual parcels, made of an infinite number of parcels. So I could sit here and draw an infinite number, but the ideas would be the same, that we're shaping this kind of what we call velocity defect. The uniform flow, I would draw the edge of the velocity vectors that look like this, just a straight line. Here, it looks like a defect at the wall here. That would be just tracing over these velocity vectors. And now you can see it's extending further in the flow like this, further in the flow like this. And we can imagine this is just going to grow with time as we go downstream. I could keep drawing this idea. If I trace together the point where the flow goes from 0, it starts at 0 at the wall, and then at some point it becomes equal to or just about equal to the free stream flow. And I would maybe put a dot there, and I put a dot here. And you can see how this is, the dot that I'm drawing is getting further and further from the wall. And I'm just going to connect the dots here with a nice little curve. Okay, so I've connected the dots. This will show up in a second. And we have the connection of dots is the boundary layer itself. Not sure why it's not showing up here. There it goes. So everything in here, so this is the boundary layer. Everything inside this pink line is the boundary layer. And this is the area in which viscous effects are important. This viscous effects being this exchange of momentum in the boundary layer. Oops, I meant to write viscous effects. Outside of this, the viscous effects are negligible, generally speaking. So outside of this, we can consider the flow inviscid. Bernoulli's is okay outside the boundary layer. Inside the boundary layer, it is not okay because we have frictional losses and Bernoulli's equation doesn't allow for those. So this boundary layer, we're going to define a distance from the wall here, delta. This will be the thickness of the boundary layer. And that delta will be a function of x, the distance from the leading edge of the plate. All right, so this is a basic cartoon of how this works. When we get to turbulent boundary layers, the idea is the same. The only difference is in which momentum is mixed. The U momentum is mixed in the vertical is done through eddies instead of Fickian or molecular collisions. So it's going to be a more rapid process, which means that the boundary layer is going to grow quicker. So let's talk about, here's a nicer drawing than the schematic I put together. I'm going to the next slide here. And so I have let's see here. It's a big delay between my iPad and the Zoom. I'm not sure why. Okay, all right, so on the next slide. All right, so this shows a nicer drawing in the schematic, but everything's pretty similar. There's different definitions of this boundary layer thickness delta. There's different versions of this. One is the one I described, which is the point where we walk away from the wall in the vertical, going into the boundary layer, and we I'm going to pause this and exit and come back in and see if I can get this to speed up. Okay, hopefully that worked. All right, so we're back here. So this is a nicer looking drawing. Again, delta is this distance. We go normal to the plate. We walk until we hit the edge of the boundary layer, which can be defined in a number of different ways. We're going to focus on one definition, which is delta 99. It's the point at which the velocity is back to 99% of the free stream velocity. And by free stream velocity, I mean here, let's say here, it's 2 meters per second. That would be the free stream velocity. Here, if you walk back here, it's 0, and maybe it's 0.25 here, and 0.5 here, and 0.75 here. And right here, we're at 1.98 meters per second. And at that point, we are at 99% of the free stream flow, 2 meters per second. And so we define that as the edge of the boundary layer. So this is easy to conceptualize. However, it's a little bit arbitrary. So why we picked 99% and not 97? But it is a traditional way of teaching and working with the edge of the boundary layer. There are other definitions that come up that you may see if you get involved in viscous fluid mechanics, displacement and momentum thickness. These tend to be utilized in turbulence formula, but they aren't so easy. They have a less kind of visual appeal. So we'll focus on delta 99. Reynolds number is the key to this, and we're really thinking about competing effects. As these fluid parcels are moving, and they're moving downstream with a velocity u. And so there's a horizontal time scale, essentially delta x over u. That's how quickly you're moving laterally. It's a time scale associated with a lateral movement of delta x at a speed u. So if you increase u, you're moving faster from left to right, and it's going to decrease the time scale to move a certain distance delta x. There's also a diffusive time scale, which momentum's diffusing in the fluid away from the wall. And this affects the growth rate of the boundary layer with time. And that diffusive time scale is equal to the square of the distance traveled from the wall divided by the kinematic viscosity. So here we see a fluid property coming in as well. And we can see when that fluid viscosity, kinematic viscosity increases, the time scale decreases. And that makes sense because diffusion is happening faster because the viscosity is increasing. So we have these two competing pieces. And what we'll basically see when we go through the actual formula associated with boundary layers is that for high Reynolds number flows, and the Reynolds number again is defined as this. So we have a general Reynolds number. It's always a velocity scale, the product of a velocity scale times the length scale times divided by the kinematic viscosity. For the velocity scale, we use the free stream velocity, which in the case of a ship will be the ship speed. For the length scale, we're going to use, for this discussion, x, the distance from the leading edge of the plate here. So we're defining this Reynolds number. We're putting a little x here just to say, hey, this is the Reynolds number as defined, with the length scale is defined as the distance from the leading edge, and we're allowing it to vary. So the Reynolds number here will be different than the Reynolds number here, be different than the Reynolds number here in this particular case, because x is changing across those between those locations. So we defining this Reynolds number, and what we'll see in the formula is when we crank up the Reynolds number, and you can think of it if you want as we're increasing U. Let's keep X a fixed location. Let's talk about, say, this one. And if we draw a boundary layer, if we have a boundary layer at the edge of a boundary layer at a given Reynolds number, let's say it looks like this. And then we come and say, hey, let's increase the Reynolds number by taking the flow from this speed. We'll increase the flow. We'll double the flow, something like this. So this is going to double the boundary layer. I'm sorry, double the Reynolds number. And we'll see the impact on the boundary layer is twofold. One is that we'll see a change in the skin friction. We're going to quantify that later. We'll see the skin friction coefficient will change. And the other is that we'll see the boundary layer will become thinner. And this is a little non-intuitive. People think about higher Reynolds number. Why wouldn't the boundary layer be thicker? Well, in fact, it's the opposite. And that's because you're basically cranking up the speed at which parcels are moving from left to right. And so, but that diffusive time scale is not changing because that depends on the property of the fluid, nu. And so parcels are just getting further along the plate before the diffusive effect from the no slip condition at the wall can get out to reach them. And so you have thinner boundary layers. For most of the work we'll be dealing with, the boundary layers are going to be at the, and actually I should also note here, the boundary layer grows with distance down the plate. So if this is the end of the plate or end of the boat, whatever it happens to be, the thickness of the boundary layer will be the maximum. And the relative thickness, meaning the thickness of the boundary layer divided by the length of the boat, or here the length of the plate, is only going to be a few percent, 1%, maybe 4%, something like that, but just a single digit percent, meaning that when you look at this thing, whatever it is, a plate, and you think about the boundary layer, I've probably drawn it here more than a few percent. Well, that's probably about right. Maybe 6 or 7% is what I drew here. It's going to be relatively thin. For low Reynolds, and this will be because we're dealing with Reynolds numbers are typically in the millions to billions, millions, tens of millions, hundreds of millions, billions. Very high Reynolds numbers associated with engineering scales. For very small Reynolds number, for example, if you have, there are, I'm just going to give a weird example, but there are barnacles. If you're familiar with those, these are little hard things that attach to rocks and can cut your fingers. They eat by putting out these little cilial nets. So they have these little hairs. They're about the thickness of an actual hair on your head. And they can wave them back and forth. And food particles are moving through the flow. Sometimes the flow is just flowing past and they can catch them. And they catch them a number of different ways. But a key thing, if we take a cut through the cilial net here, so I'm looking at a cross section of these hairs, something like this, the Reynolds number through these cilial nets is so low, it's something, I wish I could remember what it was, it's less than 1. So instead of a million, think about 1. The boundary layers are so thick that essentially the boundary layers are interacting between these cilial nets. So you have this region of dramatically slowed flow through the nets and allows them to trap these particles. And in those cases, the thickness of the boundary layer relative to that hair size or cilial hair size is much thicker than it. The percent is something like 300 or 400% versus 1 or 2%. The only difference here being Reynolds number. So we won't deal with any of this kind of tiny Reynolds number. Depending on what you do down the road, you may be dealing with smaller Reynolds numbers. For engineering type stuff, we're typically looking at 1,000,000 plus for the most part. Unless we'll do some class examples today, it'll be a bit less than 1,000,000, but certainly not 1. I'm going to skip this transition to turbulence. I'm going to talk about that on Thursday to talk about how the nature of the boundary layer can change at higher Reynolds numbers. The other key piece, other than the thickness of the boundary layer, is the shear stress. And really, for practical purposes, this is the key thing we want to take home from this. Associated with the fact that the fluid at the wall is not moving at all, and the fluid above the wall is moving faster than 0. So if in the wall reference frame, it's 0 at the wall, somewhere away from the wall, it's greater than 0. It means there's a shear in the fluid. When we think about this derivative here, the rate of change of u, and I apologize, I'm changing my coordinate system here. So y is a distance from the plate here in this particular example, and x is downstream. So the rate of change of u with respect to y, the way I've drawn it here, is positive. It's greater than 0 because u is increasing with y. And there's a stress associated with this because fluids resist a shear. So we refer to this as a shear being a change in velocity with respect to a distance coordinate. In this case, the change in the u velocity, the left to right velocity with respect to the vertical y. And it's positive in this case, and fluids resist a shear. And we can write a stress, which has units of newtons per meter squared. So this says same units as pressure. A stress is created, which is proportional to the shear in the fluid. And the constant of proportionality is, by definition, the dynamic viscosity. This is the dynamic viscosity, or what most people just call viscosity. So this is actually how viscosity is measured. You measure du dy, you measure tau, and you use that to determine viscosity of an oil, of a honey, of fluid, whatever it is. So viscosity tests actually make this formula, use this formula to compute u by having to measure the other two terms. So this tau is a stress in the fluid. And we refer this particular stress is a shear stress because it comes from the shear of the fluid. And you can think of it here. Here's the wall like this. And if I put the wall on roller skates like this, so it just happens to be on roller skates all of a sudden, and we send some fluid over this plate right here that happens to be on roller skates, we get a no slip condition at the wall here, so it's 0. And some up here, it's greater than 0. So there's a stress associated with this. The fluid is pulling the wall and parts of pull onto the wall. We refer to that as a shear stress. It is tangential to the fluid direction. So we can contrast this with pressure, which is another type of stress and has the same units, but pressure, so the fluid itself here, there's some hydrostatic pressure in the wall, there's particles here pushing. Pressure is a normal force. It acts normal to a body at all times, meaning orthogonal to the body. The skin friction, which comes from a shear stress, the shear stress is tangential or parallel to a body. So they're completely different. They have the same units, completely different mechanisms, and completely different directionalities. So here at the wall, I kind of covered it up here, but the shear stress at the wall, and again, this has units of newtons per meter squared. So it's a force per area is equal to the shear at the wall here times the viscosity of the fluid. And so the greater the shear at the wall, the greater the shear stress at the wall. And so this has implications on the shapes of boundary layers. If I think about a boundary layer like this, very sharp, and then it comes up like this, or if I think about a boundary layer that looks more like this, and when I'm looking right near the wall, because that's where I care about, there's going to be shear stresses all over the fluid, but the one I really care about is what's going on at the wall, because that imparts a force on the wall. Here, let me draw the wall in a different color and make it straight. Here is my wall. If I look in this right sense here, I'm walking away from the wall here, It starts at 0, walk, 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 zoom in here, walking away from the wall. I gotta go, the change in velocity happens over a fairly long distance before I get back to, say, a quarter of u infinity. Whereas in this case here, I only have to go a tiny distance, I can't even draw it, before I hit my quarter of u infinity, which was my arbitrary point that I was thinking about. But when you're looking at du dy for these two cases, again, the rate of change of u with respect to y, in this case here, it's much greater than the other case. And we'll see this case where it's greater is going to look more like a turbulent boundary layer. So this du dy at the wall can vary. It depends on the shape of the boundary layer, and that is directly impacting the shear stress at the wall. So it's important. Now, it's hard to quantify, and we'll go through some formulas of how we get into this, but we can see that it directly impacts it. We're going to be looking at two particular drag forces associated with these shear stress. The first is at a point in space. So if I go back to my original problem, just thinking about, probably messed it up. Yeah, this plate here. If I'm thinking, what is the shear stress happening right there at a particular point? Then I'm thinking about a point on the plate, and I can derive the properties of what's going on at that point. But then I say, oh, what about this point, a different point? What I'll find is the properties there are different. If they're downstream or upstream of that blue point, it's going to change what the shear stress is. It will vary over the plate. So there's going to be a set of formulas associated with computing the force at a shear stress, and I should say, at a point on the plate. Now, we're going to talk about those. We'll talk about the distribution. But the key thing we want to take out of this, and from an engineering sense, is we want to know the whole force on the plate. So we want to understand the distribution of shear stress, integrate that to get a force on the entire plate. Because really what we care about is the drag on this whole plate. But it's important to know something about the distribution, and there are aspects of where understanding the distribution is important, particularly when it comes to biofouling. Biofouling objects like algae and barnacles, they struggle to resist shear forces. So you tend to see stronger biofouling where the shear stress is less, and weaker where it's a higher shear stress. And we'll go through some questions related to that. So let me go back to our discussion here. So again, we're dealing with these two two different ways of thinking about this. One is what's going on at a point in space, and one is integrating the whole distribution over the plate, and it gives us a drag coefficient for the plate. All right, so in thinking about a skin friction coefficient, at a point on the plate, we're going to be dealing with this particular Reynolds number, because when we have a plate like this, and X is a distance from the leading edge, and the flow is moving from left to right, and I need to know what's going on right there. Well, I need to know how far it is from the leading edge. That's what's going to matter. And that distance is this X that's in the formula. You can see it right here. So we're going to build our Reynolds number based on that distance. And we'll talk about this when it comes to transition, and you had a quiz question related to this as well. So we'll use this REX. That REX will plop into a formula, and out will come a skin friction coefficient in the formula. This is a skin friction coefficient. It is a dimensionless stress. The actual shear stress in newtons per meter squared, or pascals, is here, tau wall, the shear stress at the wall. We can non-dimensionalize it by dividing by the dynamic pressure. So this isn't a force, so I don't have any areas in here. I just have to have a denominator with units of pressure, and we use the dynamic pressure, 1/2 rho u infinity squared. This will give us a non-dimensional thing, which is the skin friction coefficient. It's dimensionless, and it's the skin friction at a point on the plate, and it will depend entirely on the Reynolds number at that point, REX. For integrated stuff here, essentially all they do is once they come up with a formula for that, they integrate it over the length of the plate, because it's only going to be varying in the X direction. Across the plate in this direction, it won't vary, because nothing's happening in that direction. It's only happening from left to right as the boundary layer evolves in the X direction. We'll integrate this value over the plate, and it will give rise to a drag coefficient on the plate. Now, this is actually a drag related to the drag itself, which has units of newtons. And we'll see this for the case of the plate. We'll non-dimensionalize this by the dynamic pressure times the characteristic area, which is the area of the plate. In this case, L is the length of the plate, W is the width of the plate, and so we're non-dimensionalizing by that. We'll see the formulas for that rely on a single Reynolds number, which is the Reynolds number based on X, where X is the length of the plate here. So we'll refer to this as REL. Sometimes when I say RE, I'm just referring to the total plate Reynolds number. If I'm referring to a point on a specific location, I'm going to use this REX. So here in this particular slide, I've put the L in there just really to emphasize what's going on. But this, in this case, X equals L, the length of the plate. We're plugging it in here. So it's the full plate-based Reynolds number. In the case of the ship, it will be we use the ship length in that formula. And it's the length of the object, whatever it is, in the streamwise direction. In this case, L. Using this Reynolds number, we're going to plop that in a formula, and we'll see those in a second. And that will give us a skin friction coefficient here, from which I can do lots of stuff. For example, if I want to know the actual drag, given the skin friction coefficient, given the stuff in the denominator, I can compute, when I'm going to circle in blue here, this D. This will be the drag due to skin friction. And that's probably the primary thing we want to get out of this. We're trying to estimate skin friction today we're learning about flat plates. And then we're going to be applying a similar set of formula to ships. Now, ships aren't flat. They have curves to them. And so the formulas we'll be dealing with for ships, they'll look kind of the same, but they're a little bit more specific to ships. But the idea is the same. Now, this whole idea of a boundary layer growing on a plate was examined by several folks, including most notably Blasius here. So this is going early 19-teens, I would say, 1915, somewhere around there. He was looking particularly at laminar flow, moving over a plate, making measurements, adjusting flow speed, adjusting the plate length, adjusting the fluid viscosity, and seeing that there was a similarity similar to what Freud saw. They knew there was a similarity to things, meaning when what they called was the Reynolds number was fixed, it seemed to fix all the properties of the boundary layer. So what Blasius did was solve for a closed form solution of this. This is an actual closed form solution of the Reynolds average, or I should just say, not Reynolds average, the Navier-Stokes equations. He took the Navier-Stokes equations for 2D steady flow, and then made a couple other assumptions that you can argue about boundary layers, namely that the U velocity changes more rapidly in the Y direction versus the X direction, that changes in the V velocity, the vertical velocity are relatively small. You can hand wave a bunch of terms out of the equation. Once he did that, he achieved a closed form solution for the boundary layer, a beautiful one. And we refer to this as a similarity solution. He had to argue how things vary. So he argued that the thickness of the boundary layer, delta, which we know to be a function of X, that the relative thickness, meaning that delta divided by X at a particular location on the plate, scaled as 1 over the square root of the Reynolds number. So he made these arguments based on physics arguments similar to that time scale ratio we looked at earlier. And then he was able to achieve a solution where he came up with a relationship between a non-dimensional, so this is a non-dimensional distance from the wall. So you have to kind of turn your head and think about this being the distance from the wall here. And this is the velocity field. So I'll draw as if they're really velocity vectors moving like this. This is the velocity vector. We can see that at the wall it's 0. Far out here, when eta equals 7, we're back to the free stream. It tends to even out, and we're back in the free stream flow. So you can think of this. I don't think you might have had to go sideways. Let's see. Nope, cannot do that. Sorry. So we can think of this as a boundary layer, just drawn differently. So this is our velocity, but it's non-dimensionalized. So it's whatever the velocity is, and U here is a function of the distance from the wall, y, normalized by the free stream velocity u infinity, and we have this non-dimensional coordinate, y coordinate here. So eta equals y, the distance from the wall, times u over nu x, the square root of u over nu x, and which has units of length scale. So this is a non-dimensional distance from the wall. When you do this, all the measurements, every measurement that is made, and you can see that all these measurements, these little dots and squares, these are different experiments running at different Reynolds numbers at different locations on a plate. Could be different fluids, could be different flow speeds, different locations on a plate. And you're drawing if you take your physical measurements of u as a function of y, and you take your physical measurements of y, the distance from the wall, you'd have all kinds of data. But if you put it into this non-dimensionalized system, they collapse. You can see how it just collapses onto Blasius' solution as that dark line that runs to this data. So he was able to collapse reality into this simple space, a beautiful simple space, which means that ultimately he wrote this: a non-dimensional distance from the wall is a function of the non-dimensional flow speed, or vice versa. So there's been some upgrades to this over the years where they've kind of removed some of the simplifications that Blasius put in place, or to account for varying pressure and other kinds of things. But this is still really fundamental to the work. So some implications of that. These are the resulting formulas that comes out of his solution. They're closed form, relatively simple formulas for three key things. One is a boundary layer thickness, one is a local skin friction coefficient at a point, and the other is the drag coefficient due to skin friction, all for laminar flow. So this assumes laminar flow. We'll talk Thursday about whether we can assume laminar flow or not. Today, we're going to be assuming laminar flow. You can see here that the relative thickness of the boundary layer, this first formula, scales as 1 over the Reynolds number. Happens to be a 5 there, but it scales as 1 over the square root of the Reynolds number. Our local skin friction coefficient here scales also as 1 of the square root of the Reynolds number. Different coefficient in the numerator, but that's not a big deal. And also the total drag coefficient scales as 1 over the square root of the Reynolds number. So we can already see here a couple things. Most notably what I talked about earlier, as you increase the Reynolds number, the boundary layer gets thicker. You can see that right in this formula. If you make this numerator bigger, meaning the Reynolds number has gone up, then the thickness of the boundary layer is going to go down. And we'll look at some solutions of that later. So all these formulas scale as 1 over the square root of the Reynolds number. We'll see the turbulent boundary layer formulas do not scale the same way, not surprisingly. Just different coefficients here. You don't have to memorize them. You can refer to this worksheet if you want. And if I give this such a question on the exam requiring this, you'll see these formula there, because I don't expect you to memorize those numerators. I do want you to think about this idea that it scales as 1 over the square root of x. So some key implications of that, I rewrote the formulas here. These are the same formulas of the previous page, just plotting them here. When we think about the boundary layer thickness as a function of x here, we can plot this formula here for a given Reynolds number, 100,000. I picked 100,000. Here's non-dimensional distance along the wall, x over L. Here's delta 99 divided by the plate length here. And you see this nice kind of boundary layer here. If I solve for delta 99 in this formula, I have delta 99 equals 5x over square root of Reynolds number based on x. And if I go through the math, I'll find out that this is proportional to the square root of x. It tells me that the boundary layer thickness, the dimensional boundary layer thickness, scales with x positively, meaning it grows. We already deduced that earlier. But the functional relationship between distance downstream of the plate, x, and the boundary layer thickness is a square root function. So it looks like a square root function as plotted here. That looks like square root of x. So it'll grow as square root of x. We're going to contrast this with the turbulent boundary layer Thursday, where we'll see it grows much faster than square root of x. So this is a square root of x form. And if I were, and maybe I should have done this, plot this at a higher Reynolds number, say 200,000, you would see it look more like this. I don't know exactly what it looks like, but I'm going to call this 200,000, just so you have a sense of, if you increase the Reynolds number, hey, what might happen? The other piece is the local skin friction coefficient, which I've plotted here. This is non-dimensional already. It's a function of non-dimensional distance along the plate. I picked the same Reynolds number of 100,000 here. And what you see is the skin friction coefficient is highest near the front of the plate, and it's lower as we go downstream. And the reason for that is related to, let's just do a quick aside, this wall stress is equal to, again, the viscosity of the fluid, mu, that's supposed to be mu, times du dy at the wall. It's times that shear at the wall. And when you have a plate here, and you have this uniform boundary layer coming in like this, that moment it hits the plate, and that no slip condition affects just the near wall case, your velocity defect has a very sharp interface, just initially, very sharp, like this, because the rest of the flow hasn't heard about the plate slowing it down yet. So you have a large du dy here, a large shear. You walk a little bit away from the wall, and the velocity increases from 0 to almost infinity right away. Large du dy means large shear stress, tau wall, and it also means a large non-dimensional shear stress, so large CF. So that is near the wall. By the time we get down here and things have relaxed, we went through the whole drawing earlier, so I won't redraw it, but things have kind of relaxed in space. The boundary layer is thicker like this. And now we have the slope. Think about this slope here. And this is y, or this is y, and this is u. So du dy is the inverse of that slope. Here is a relaxed du dy, which means that tau wall is smaller and CF is smaller. So you can see how as we go down the plate and the boundary layer relaxes, grows, it relaxes this condition at the wall. And this gives rise to this distribution that we see drawn out here analytically from Blasius' solution, where you get this maximum skin friction at the wall. Now, if you look at the formula, you say, well, there is kind of a problem, because as x goes to 0, meaning we go to the leading edge, CF is going to go to infinity. And we know we can't have an infinite skin friction right at the leading edge. That doesn't make any sense. That would mean the drag was infinity. And the reality of this is this formula fails right when you get to the leading edge. And that's because the assumptions that Blasius needed to come up with the closed form solution, they fail at the leading edge. And so his solution failed at the leading edge. So his solution produces incorrect results at the leading edge only because he had to make certain assumptions to solve this, and those assumptions don't hold at the leading edge. So normally what you do is kind of ignore the very beginning here. So if you were asked what's the skin friction, a millimeter from the leading edge of the plate, you probably would not get away with using Blasius's formula. So we won't be asking that. We'll be focusing here, we'll look here, something like that, all in very valid locations. And the integrated value is still okay, because it only skyrockets very close to the leading edge, so over a very small area. So the integrated value is still correct, or almost exactly correct, compared to the real fluid. So in terms of the approach that we'll be using, I'll just talk it through here, and we're going to run through some problems in a second. This is for total drag. So we're getting away from, hey, what's going on at a point, to what's the integrated effect of this shear stress. We use the formula from Blasius's three equations. Let me go back to them so you see them again. Two are at a point here. These two are at a point in space, which could be at the trailing edge. So if I asked what's the boundary layer thickness at the trailing edge, you would just put, L here in the formula and compute your Reynolds number based on L, and whatever you got for delta 99, that would be the the boundary layer thickness at the trailing edge. Same with this one. It's at a point, which could be the trailing edge, could be halfway back, whatever. You just got to pick your correct X. This one, oh my goodness, I'm realizing I made a mistake in this formula, and I'm terribly apologetic about that. This should be Reynolds number based on L here. So in this case, the integrated skin friction, I guess I take it back. So we could use X. This would be integrated to the point of X here on the plate. I don't know why you'd care about the skin friction on the plate up to some point. So generally speaking, you're putting X equals L into this formula because you care about the whole plate. So this is for everything up to the point X. We're integrating all the skin friction that's happened before there. So it includes the strong skin friction at the front and it's weakening as you go down. This includes all those effects. So we're going to use this formula when it comes to drag on a plate. Here it is again. And then what I care about is the whole plate. So I'm going to set X equals L in that formula. You can see it here. We'll get the Reynolds number based on the whole plate. So if this is a 1 meter plate in the streamwise direction, it's 20 centimeters wide. It's water moving 0.1 meter per second. So I have the velocity. I have the plate dimensions, including the key dimension, which is the streamwise dimension. The width we'll just see, it just becomes a multiplier. If the plate's twice as wide, the drag goes up twice as much. If you make that plate longer, say twice as long, it doesn't double the drag because it changes the Reynolds number, and the relationship of drag coefficient and Reynolds number is not linear. So it won't just double the drag. Here we would compute the plate-based Reynolds number, the flow velocity times the plate length in the streamwise direction, L, divided by kinematic viscosity for water, 1e to the minus 6. We get 100,000. We'll find out Thursday. This is a laminar, likely a laminar flow, just based on its lower Reynolds number. Then you plop that in the Laplace's formula, you get its drag coefficient. Here it is. And you can see it kind of looks like the drag coefficients we've already been looking at in quizzes and stuff. A couple of zeros there before you get to the number. So this is another one where you might see that times 1,000 business, right? To try to make it a cleaner number. And here it would be 4.2. They would write 4.2 and then they'd say times 1,000, meaning it was multiplied by 1,000 to become 4.2. The actual one coefficient is 0.0042. Then we dimensionalize it by multiplying by this number here. And I'll just write the CF here is equal to the drag, the friction drag on the plate divided by 1/2 rho U infinity squared, the dynamic pressure, times the plate area, S, where S is equal to length times width here. And so now I'm going to dimensionalize it. So I want to solve for DF. CF comes from Blasius's formula. And then we multiply by the denominator here, 1/2 times 1,000, which is the density of the water, times the velocity squared, 0.1 times 0.1, times the plate area here, 1 meter by 0.2 meters. And we get whatever it is in newtons, some kind of small number in newtons. This would be flow over one side of the plate. If there happened to be this plate was somehow hovering in the flow, it wasn't on the seabed, it was just swimming through the flow somehow, so that there are boundary layers on the top and the bottom, I would then have to multiply this by 2. You can think of this two ways. One is, hey, I just computed the drag on one side of the plate using this formula, but really it's affecting both sides of the plate, so I'm going to multiply it by 2. Or you can think of it as coming back in and saying, I've computed my drag coefficient, multiplied by the dynamic pressure, and then multiplied by the area of the plate, which would be 1 times 0.2 times 2, because we have to account for both sides of the plate. Either way, you get to the same number. You can think of it either way. So let's go through some problems just to get some sense of scale of what's going on here. We're starting with this AUV here. Some dimensions about it. So it's not here it is being lowered or raised into the water. Not sure which way it's going. We're saying it's going at 2 meters per second. And we're going to be talking about the flow over these control fins. And I picked these control fins because their length scale is relatively small, because they're small. And that will keep the Reynolds number down into the laminar range. There isn't a lot we'll be dealing with this semester where the Reynolds number is low enough that we'll be thinking laminar flow. Most of our work is going to be dealing with turbulent boundary layers. But this class is about laminar, so I had to pick something that would generate relatively low Reynolds numbers, which for engineering stuff means control surfaces like this. Or we could have used this mast here. That would have been okay too. But we're going to use these control fins here that help orient and steer this particular thing. This uses an X system. You see X and pluses. We'll talk about this later in the semester. In the context of submarines, what's better, but it applies to AUVs as well. And I'm just going to grab one of these and rip it off, and we'll be talking about it over here. It's going to look something like this, and we're going to simplify it to being more like a rectangle. So that's a control surface. and the flow is moving like this across this particular flow surface. And it has dimensions of, maybe I'll draw it right here. I'm going to redraw it here, and I'm going to draw it in the same sense I like to draw stuff with flow moving from the left. So here's a control surface. I ripped it off the boat. The dimensions in this direction are 0.1 meter, and the directions across the flow are 0.15, like this. Obviously, it has flow on both sides. So this is a case like we just talked about, where you have a surface with flow on both sides. Flow is moving from left to right across this thing. And we are going to ask, let's see, what's the appropriate Reynolds number? If we're thinking about boundary layers on this thing, what's the appropriate Reynolds number? And remember, Reynolds numbers are always a velocity scale times a distance scale divided by a kinematic viscosity. For the velocity scale, it's just going to be the free stream flow speed, which was what, 2 meters per second. And for a length scale, we have to use the length scale in the streamwise direction. Right? There are the length scales to this problem. This transverse direction is 0.15 meters, but that's not relevant to the development of the boundary layer. So we do not use that one. We say L equals 0.1 meter. And the kinematic viscosity will stick with our sort of nominal 1e to the minus 6 meters squared per second value. And if we put this together, we get a Reynolds number, and I'll put an L here, but I might skip the L later. Reynolds number based on L, we get a value of 200,000. What we'll see, I'll just give you a little preview. On Thursday, when you do prep for turbulent boundary layers, we'll see the rule of thumb, and I think we may already had a computation related to this. The rule of thumb is that when that Reynolds number of L is greater than 500,000, then, actually, let me say it this way. When that rule of thumb is when the Reynolds number based on L is less than 500,000, we can assume that the boundary layer is fully laminar. Fully laminar. So in this case, if I were to say, oh, I got this problem wrong, the AUV actually travels 10 meters per second, or 5 times as fast, this would result in a Reynolds number of 1 million. Now, Reynolds number of 1 million is going to be tricky because it reaches 500,000 about halfway along, and that means it's kind of a mix of laminar and turbulent, and we'll talk about how we deal with that on Thursday. This case, we are well under 500,000. I think it's safe to assume it's fully laminar. We're going to use Blasius's formula. Oh, I already gave you the other answer here. So because Reynolds number based on L less than 500,000, we're going to say laminar. Now, we don't know this for sure, and there are some things that affect laminarity. The two key ones are how rough the wall is. If it's covered in rust or whatever this control surface, probably fiberglass. So let's say it's got divots on it or barnacles. And that can trigger turbulence earlier than 500,000. The other thing it depends on is when we have our boundary layer, or like I'm drawing a side view again, there's the boundary layer forming. The flow itself, we've been drawing it as having perfectly beautiful uniform flow, but the reality of the ocean is not perfectly uniform. There's lots of little turbulent eddies all the time in the free stream flow. And we refer to this as free stream turbulence, little eddies that exist all the time because nothing clean about the ocean water. And so the level of this free stream turbulence can impact this transition of this movement from laminar to turbulent. So those are the two key things it depends on. We're going to use, unless given otherwise, a rule of thumb of 500,000 is our trigger. The only time I think that we'll deviate from this is when we're dealing with ship models. What they do in ship models, if we have a full-scale boat, the Reynolds number, let's say it's 1 billion, it's a giant oil tanker, and then we have a tiny model for it, and we put it in the water tank, and we realize that the Reynolds number is small. So let's say it's 400,000, and we say, oh boy, not only is our Reynolds number wrong, which is there's nothing we can do about that, the flow, our boundary layer on our model is not even turbulent. It's the wrong Reynolds number and it's the wrong regime. We're going to see what people do is they put little things on the front of the boat. They're called turbulence stimulators. Usually sand strips, broken glass, just roughness. That's all they are. They provide roughness, and they can trip the boundary layer and cause it to be turbulent even at low Reynolds numbers. And so this is a trick they play to say our Reynolds number is still wrong. We can't change the Reynolds number. However, we might be able to influence whether the boundary layer is turbulent or not by these roughness strips. These are very commonly used. So we'll come back to that later when we talk about model testing, but just keep that in your brain between now and then. So what's the thickness at the boundary layer of the trailing edge? All right, so we're going to go to Blasius' solution to get this. I'm going to draw the side view again of our control surface. I'll give it a little thickness because it has to have some thickness. And the flow is coming in like this. And this again is in this direction, it's 0.1 meters, and the transverse direction is into the board now from the way we're looking at this is 0.15 meters into the board. And there's a boundary layer forming. We've already argued this thing out, and it's growing with distance downstream. And what we're asking is at this particular location at the trailing edge of the plate, how thick is it? And this will be the thickest it will be. It starts from 0, goes to some thickness, whatever it is. Now we're going to use Blasius' formula for, and again, because it's under 500,000, we use a laminar formula. So go to Blasius. We have for his formula for a boundary layer thickness, we have the relative thickness, delta 99 divided by x equals 5. And again, everything depends over we see our key dependence on the square root of the Reynolds number. But what location do we care about? X equals L. So we're at x equals L, which happens to be 0.1 meter. So let me just rewrite this formula in that sense. So I have delta 99, physical distance in meters, is equal to 5L divided by square root of Reynolds number based on L. We already computed that Reynolds number in the prior part. So this would be 5 times 0.1 meter, that's L, divided by square root of 200,000. That's the Reynolds number based on L. We already computed it, and we get a value of, apologize, trying to find it here. We have a value of 0.0011. So that's the meters. So it's 1 millimeter, roughly, 1 millimeter at the end of a 0.1 meter plate. So we can see here, did I do this right? Yeah, so it is, yeah, so is 1 millimeter here after 0.1 meters here. So we have 10 centimeters and a 1 millimeter thickness boundary layer. So this is, let's think about that way. It's easier to think about this. 10 centimeters this way, and almost exactly, not quite, 1 millimeter this way. So this is the physical distance. This is delta 99. Just thinking of the relative thickness, if we do delta 99 divided by the length of the plate, so I'm going to divide this by 0.1, we get 0.011. Basically 1%. It's a 1% thick boundary layer, which is pretty thin. You can see I drew it, did not draw it correctly. I'm going to go back and try to fix it. I don't know how to draw 1%, but I'll try. One's probably, maybe I can't even do it. Maybe here. So it's pretty thin. By the time we get to the back, relative to the length, it's about, that's probably even too thick there, but something like that. You can see how thin this viscous region is in this particular case. It's pretty thin. So something like 1% thick for a Reynolds number of 200,000. So out here, the flow is really inviscid. It doesn't know about the boundary layer. It doesn't know about the plate. There's no viscous effects. Doesn't matter. Within that boundary layer is where all the viscous effects are. What about the thickness at the halfway point here? So you might be tempted to say, well, if it's a millimeter at the end, maybe it is just, it's maybe just half that. Why don't we just say half that? But it grows as the square root of x. It doesn't grow as x. It doesn't grow linearly. So it's not so simple. And if we were to compute this, we would basically go through the same math, but we'd use a different length scale. Delta 99 over x equals 5 over the square root of REX. Now x is different. X equals L over 2 equals 0.05 meters, 5 centimeters, instead of 10 centimeters. So a different number here. And I would plug that in, equals, and I would say delta 99 equals 5 times x, which is 0.05 meters, halfway down the control surface. And the Reynolds number there is not the same as the plate-based Reynolds number, equals u times 0.05 meters divided by 1e to the minus 6 meters squared per second, and that'll be 100,000. The Reynolds number halfway back is 100,000 because it's trailing edge, it's 200,000. And this is square root of 100,000. And we'll get a different value, which I didn't actually compute here, but it's going to be thinner, but not half as thin as the trailing edge one, because it isn't increasing linearly. It is going as a square root. So the functional form means it's not a simple calculation. How about the shear stress at the trailing edge of the plate? And again, if we go back to here's our plate. When we talked about shear stress distributions, they were maximum at the leading edge and they decayed with distance downstream. We're asking what's the shear stress at the trailing edge. This should be the minimum shear stress that we're going to see on this plate. The highest is at the leading edge. The least is at the trailing edge. For this, we'll use a different set of formula. So we go back to Blasius. We're dealing a laminar case. We have CF equals the shear stress in newtons per meter squared, or pascals, divided by the dynamic pressure, which we're going to have to compute if we want to actually get the dimensional stress. And this is, according to Blasius, equal to 0.664 divided by the square root of the Reynolds number based on x. Everything's divided by the square root of Reynolds number based on x. And so, but my x equals L at this case because I'm asking specifically at the trailing edge when x equals L. Therefore, REX equals REL equals 200,000. We computed that in the first part. So I have everything I need here. I have CF is going to be equal to 0.664 over the square root of 200,000, which is how much? See if I actually computed that. Yep, 0.0014. 0014. That is the shear stress coefficient. It's a dimensionless shear stress at the point on the plate, a particular point right there. So this doesn't apply to the whole plate, just a single location. And then I can compute tau wall from this equals CF times the dynamic pressure. So I'm just dimensionalizing this into a shear stress, and I'll get a value of about 3 newtons per meter squared. This is sometimes known as a Pascal. The same units of pressure, of course. So that is the stress right at that location. And you could find out if you're dealing with biofouling, you would know that certain algae can resist up to a certain shear stress. Let's say they can resist up to 2 newton per meter squared. Then we might say we're not likely to see that algae at this point in the hull. Is the shear stress at halfway down greater than at L? This is a general discussion question, but let's rely on this figure here. I've already drawn the distribution. And the fact is, for one regime, in this case laminar, its maximum, it decays with distance downstream. So it would be greater at L over 2 because it's upstream of L. So I'm going to say yes. I'm not going to run through the math. See if I actually put it in the solutions. No. So it is greater at L over 2. And this is because the shear stress drops as you go down the plate. Now we'll get to an actual engineering computation. What's the drag on this thing due to skin friction? This goes to that last slide I put in the lecture notes, but basically that kind of how-to map. Now we're dealing with the Blasius's third formula, which is the drag coefficient due to skin friction, 1.328, same functional dependence, square root of Reynolds number based on L, the plate length. We already have everything we need. That's 200,000 is that Reynolds number. So 1.328 divided by square root of 200,000. And I get a value of 0.003. So there's a drag coefficient. It's roughly, 1 over 1,000. Here it's 3 over 1,000. And I can dimensionalize this. I'm going to say the total drag is equal to, and let me write the general formula and then we'll fix it. So we have CF equals the total drag divided by the dynamic pressure, 1 over 2, 1/2 here, rho u infinity squared times the plate area here times L, the length in the streamwise direction times the width, the transverse width. Cat's making a strange noise. And then we have DF equals CF. I want my dimensional stress, shear stress. Rho U infinity squared, eventual drag, I should say, times L times W. So I can plug that in, but I really need one other factor because the flow is moving on both sides of the plate. So I need to multiply this by 2 because there's 2 sides of the plate in this case. This is specific for using flat plate skin friction formula. When we use other formulas, I'm going to try to be very clear about how we handle the side business. We're using flat plate formula. We're dealing with 2 sides of the plate. We need this factor of 2 here. We have everything we need. Did I say it was fresh water, or what did we decide to do about that? Don't think I mentioned that. Let me see what I put in the solution. I use seawater density. So I'm going to say rho equals 1,025. When you're dealing with seawater, that's a good number to use, kilogram per meter cubed. So it's a little more precise than 1,000, which is a freshwater value. The ocean, of course, varies depending on salinity and temperatures we talked about in the second lecture. 1,025 is a good nominal open ocean value. We have everything we need. I'm running out of room here, I apologize, but we have DF is going to be equal to 0.1845 newtons. That's what I get when I put everything together. So this is the drag due to skin friction on that plate. It's the only form of drag on this plate. Where'd my plate go? Yeah, it's the only form of drag on this plate. If we assume it's far from the free surface, so there's no relationship of this and the free surface, and the plate's essentially infinitely thin, the only drag can be tangential to the plate, the surface tangential to the plate. The only form of drag that's tangential is skin friction. So this will be the drag on that plate. Now we're dragging it along. If we assume a propulsive efficiency of 50%, so we'll get into this when we talk about propellers. This would be not a great propeller, but something about the ballpark okay. So you put a lot of energy into turning that propeller, but only 50% of it actually goes to useful work of pushing the boat forward. So we're saying it's 50%. So let's say we have 4 of these control surfaces, and we have to drag them 10 kilometers. And we're trying to figure out how much energy this is going to take, knowing that we're losing 50% of it to not being propulsively useful. And we're trying to figure out how much battery energy is going just to dragging these control surfaces, not the fuselage of the vehicle itself, which is probably going to be a greater source of loss because just simply because the surface area is more. All right, so we have energy equals a force times a distance. We got a distance scale here, which is 10 kilometers. And this energy is, and we can compute this as energy equals our drag force. So I'll just put DF here. So that's the drag force on one control surface. I'm going to multiply that by 4 because there are 4 of them. So that's the total drag here. The distance is 10 kilometers. So that's 1 e to the 4 meters. 10 to the 4 meters is 10 kilometers. And I'm going to pull in DF from the prior part. And then I'm going to multiply this by 2 because or why don't we do it this way? Let's divide this by eta, which is the efficiency of the propeller, which is going to be the same as multiplying by 2. We're dividing by 0.5 because we basically need to double the amount of energy because half of it is wasted not propelling, not moving this vehicle forward. And I think I have everything we need here. I'm going to just plug in our actual drag in newtons, 1845 times 4, because there's 4 of these things, times the distance we got to drag these things, 10 to 4 meters, divided by 0.5, because we're dealing with some losses in the propulsive efficiency. And we got about 14,760 joules. And if I convert that to watt hours, which is kind of how batteries are normally sized, we got 4 watt hours. Oops, it's badly drawn, apologize. 4 watt hours of energy. So there's an energy calculation. We won't be doing too many of those in class, but it's useful, particularly in the AUV world. They think a lot about energy because the battery has a fixed amount of energy, and that your mission, you have losses just due to propulsion. propulsion's overcoming the hydrodynamic drag forces. So that's one set of losses. Then you have what's called the house losses, and those are dealing with whatever systems are running on board. For AUVs that are dealing with sonar and other things that are really, really energy intensive, sometimes that's the dominant form of energy consumption. Depending on other sensor sets, it may be that the propulsive, the hydrodynamic resistance is a dominant form of energy loss. It really depends on what you're doing. Let me end it here. Please, hopefully you've gone through this before Thursday. We're basically going to be on Thursday talking about turbulent boundary layers. We'll contrast them with laminar boundary layers. We'll have a different set of formula that come from the work of Prandtl. They have a different look to them, but the idea is the same, that we're going to be looking at thickness at a point, shear stress at a point, and total drag due to skin friction from a turbulent boundary layer. And then we'll look at the case where we have control, where we have Reynolds numbers that imply that the early part of the item or object is laminar and the latter part is turbulent. So you kind of a mixed regime, and there's some formulas that we'll work with for that particular case. So we'll start off on Thursday talking about an Ohio class sub here. They have very similar looking control surfaces. You actually compare. An AUV is essentially like a mini submarine in a lot of ways when you look at it. They use actually this as an X configuration. The Ohio is a plus, I guess. Yes, the Virginia is an X. So anyway, it doesn't matter. But so you have a control surface here. And we'll see when we go through this, it's kind of the same thing, but what's distinctly different about it is the Reynolds number. The Reynolds number, of course, is bigger for two reasons. You have UL over nu. They're floating through the same water, so nu is the same. But when you think about a Ohio class sub, it's going much faster than that AUV, and the surface itself is much bigger than the AUV surface. So this will mean much higher Reynolds numbers, and it will throw us into the turbulent regime. So I'll end there. I'll see you Thursday.